Welcome everyone to the Stat Division's ASQ Stats Division webinar today. We've got a great webinar coming up on MSA and CPK and their relationship. We're lucky to have JD talking today. She gives lots of presentations. She's the VP of Quality in the Electronics and ADAS portion of the ZF group, and very well versed on MSA and all those things related to it. If you have questions during the talk, please put them in the chat and we will read those off for our presenter at the end of the webinar, and so you can get all your questions answered. And if you have technical issues, put those in the chat as well. I'll be monitoring and can answer things on that right away. And with that, I'm just going to turn it over to JD and let her go.
Hey, thanks everybody. I'm here this week at the SWE, the Society of Women of Engineers Conference. There's 20,000 of us female engineers running around like crazy. It's been amazing so far. Hope to see you guys all soon at some of the ASQ World Conference or Lean Six Sigma Conference, or even the Stats Conference if you guys have one. But I'm very active in the Quality Management Division. So let me see if I can get this going here. There we go. So why are we here today? We're going to do a rapid, high-level overview of how process capability generally works. So I would like you to have a calculator and paper handy. We will be interactive. This way you can follow along and see how the math goes along. From there, we'll do a quick review of the variables portion of measurement system analysis, MSA, from the Gage Repeatability and Reproducibility side of it, the GR&R perspective. We're not going to get into the statistics, I'm so sorry, of how to do the percent Gage R&R calculation, whether you use range, ANOVA, whatever formats are used. But we're going to connect the two from the percent tolerance aspect to see how an effective process capability is needed together with a gauge study. So we're going to be using these two diagrams a lot, the process capability diagram you see on the left, and then the bullseye on the right. So let's talk about process capability, CP or PP. It's a customer's quick index or a way of identifying if your process is giving you all good product. And it's a ratio. It's a ratio of the width of the process to the width of the specification. So first we need the width of the spec. And in this case, I have a spec of 0 plus or minus 10. So the width of that, so I'm going to get my pointer going here for a moment. Let me see this. Pointer options, laser pointer. Yay, I got a pointer. But we're going from minus 10 to positive 10. And to get that width, it's 10 minus a negative 10. So that total distance is 20. And now I want to have the fun part and see how fat is my process. Now I've got these parts that I've measured down here. And I've taken 20 samples. I've got 20 readings, and they range from 2 to 8. So my lowest value that I pulled out was a 2. My highest value I pulled out was an 8. I got 4 4s, 4 5s, 4 6s. And this is the distribution that I'm looking at. So now what I want to do is I want to get a statistical characteristic to see how big this process really is. And first thing I do is I calculate the average. I'm going to take all 20 of those values, add them all up, divide by 20, and I get an average of 5. The next thing I do is I actually get my standard deviation, my sigma, and I'll show you how to calculate that in a little bit. Of course, I do expect this audience to know that pretty well. Anyway, I want to take and figure out the right-hand side of my process. Where statistically does my process typically end? So I'm going to take the average, which is 5, and I'm going to add to it 3 times sigma, 3 times that standard deviation. So 3 times 167 will round off to 5, and then 5 plus 5 gives me 10. And that's where my upper tail ends. That's where my upper tail hits. Now it's a wonderful coincidence that my upper tail ends right at the spec line, ends right at the 10. But in this case, what sigma is telling me is that if I keep taking samples, if I keep measuring parts, I will find a 10. Eventually, there's going to be a 10 in here, but I've only found an 8. So these parts that I haven't found yet, they're somewhere in the box or somewhere in the future of the production run based on these 20 values. I'm going to do the same thing on the flip side, on the left-hand side. I'm going to do the lower tail of the process. My average, again, my average is minus 3 sigma, so my average is 5. And I'm going to subtract 3 times the standard deviation. 5 minus 5 is 0. And this happens to end up right in the middle of the spec. So the whole width from tail to tail, from end to end of my bell is running from 0 to 10. And there are 6 sigmas in there, 3 on the right, 3 on the left. And those 6 sigmas at 0 to 10 fits inside of my spec line twice. But one thing we have to keep in mind is that when we're dealing with this normal distribution, with this estimated bell, we're not taking 100% of all of our readings. So this, I call this the bellbrella. That's a JD term. You won't find it in any book yet. But my bellbrella covers 99.7% of my stuff. It's going to cover from 0 to 10. And those are where my parts are going to be. However, it's not 100% all of my stuff. I'm going to have roughly 3 parts per 1,000 that'll fall outside of these tails. No matter where my bell is positioned, I'm going to have about 3 parts per 1,000 outside of my tails. On the right-hand side, that's a problem because my tail happens to stop at the upper spec line. So I'm going to have half of those 3 parts, 1.5, out on the upper side. It's going to be out of the tail and out of spec. On the left-hand side, I'm still going to have that other 1.5 out on the left-hand side, out of the tail, but way within the spec. So you have to be able to remember at all times that your bellbrella, your normal distribution, it never covers 100% of your processor results. It covers 99.7% of them if you have a normal distribution. And this, again, is if you're taking samples. If I did 100% of all of my parts, then this would be a little bit different. So now if my process is shaped like a bell, and there's enough points to see normality, to see that it looks like a bell, I'm going to take my process capability. The formula is my upper spec minus my lower spec, 10 minus a negative 10. That's going to give me 20. And I'm going to divide it by how fat my bell is. My bell runs from 0 to 10. That's 6 sigmas, or 6 times sigma. And 20 divided by 10 is 2. So my bell fits in there once, twice. And that's a nice, handy thing to know. My bell can fit in there 2 times. And that's helpful for us. And we still remember that you're going to have those 3 parts per 1,000 hanging out on either side. Now we go to our next level, and we're going to see how the process is centered. Because while I can have a good ratio here, and this bell can fit in here 2 times, it's too close to the edge. And that's not the end of the story. So I do have to keep in mind where the process is positioned. And we can see clearly here that my process is not in the middle. It's on the right-hand side. It's on that 5. And it's a ratio now between the average and the spec line. So now I'm going from 10 to 5 instead of from 10 to 10. But my distance is now quite a bit smaller. I'm going from the average to the spec line. So my 10 minus my average is 5. And I'm going to still divide it by half of my process, which is 3 sigmas. So it's the upper spec limit minus the average divided by 3 times sigma. So 10 minus 5 is 5. 3 times my sigma of 167 is 5. And 5 divided by 5 is 1. So this half of a bell fits inside of that distance 1 time. And we all know already that I'm going to have that 1.5 out of there. That's going to be a problem for me. That's why a CPK of 1.0, where it only fits in there 1 time, isn't good enough for most of us. Now let's look at the other side. On the other side, I've got my average. And now I'm going to look all the way over here to my minus 10 to that other spec side. So I'm going from 5 to minus 10. So it's my average minus my lower spec limit, 5 minus a negative 10. That's a distance of 15. I can drive a truck through that thing. I'm still only going to divide it by this half of the bell, these 3 sigmas on the left-hand side. So 3 times sigma is 5. 15 divided by 5, this fits in here once, twice, thrice. Fits in there 3 times. And we got to remember that that part and a half is always going to be hanging out there. So one thing I always find with engineers that are college educated, when they learn how to apply specifications to their various features, they usually run with a plus or minus 3 sigma designation. They don't recognize that 4th sigma, or these other parts that are hanging out here. They don't recognize and realize that there's real parts out there. And if you're making a safety product, or if you're in the food industry or automotive, military, aerospace, if you're in any of those safety industries, this can be problematic because your engineers can actually use their information to create specs that don't allow you to succeed in the manufacturing process. And I see it all the time. It happens a lot. So now we're going to talk about this distribution for a few moments. We see here the spec lines. These are heavy, dark spec lines. I've got my upper spec limit, my lower spec limit, and I'm going to look to see how my normal distribution is spread out across my standard deviations. If it's normally distributed, this hangs in pretty well. Within plus or minus 1 sigma, I'm going to have 34 and 34, or 68.4% of my stuff. That's a lot of my product, more than half. And it's more than half because the bell isn't a rectangle. I'm not going to slice this up into equal portions. You can see that there's an exponential curve going down here. So it goes down pretty fast after that first sigma. And this is where all of your parts are hanging out. This is what, where they're sitting underneath your bell umbrella, the bellbrella. Within that second sigma, we've got another 13.6% on each side. In total, between plus or minus 2 sigmas from your average, you've got 95.6%. That's really a lot of stuff. That's pretty good. If I'm not making a safety product, this might be just okay. If I'm making ink pens or shirts, fabric industry, something where the product isn't safety critical, that might be good enough. When I get to my third sigma, I've just got a smaller amount of stuff left over, 2.1% within that third sigma range, 4.2 totally in the two ends of the 3 sigmas. From tail to tail, that's going to give me my 99.7%. And as we all know, my bellbrella doesn't capture it all. I'm going to have 0.15% out of my tails on either side. And in this case, because my bell is sitting right on my spec lines, I'm going to have 3 parts per thousand out of spec every time. The standard deviation acts like a law of nature. It's going to, you see it all the time. It's not an exact science. Nevertheless, your laws of probability are you're going to have 3 parts per every 1,000 you make that are going to fall outside of the bell, so long as you're normally distributed. So now let's fix some things on our bell. Let's put the bell on a diet. There's 6 causes of normal variation: man, machine, material, method, measurement, environment. We fix one or more, or we address one or more of those 6 things. You're going to notice that the spec lines will stay in the same place, but my bell's going to get skinnier. Yay, she went on a diet. So now you can see that my bell is skinnier, but my proportions are still the same. Within plus or minus 1 sigma, I still have my 68.4% of my stuff in this blue range here. And that's a lot tighter. My parts are a lot more closer together because my process has less variation. The 13.6 are still in that second sigma range. My 95.6 now, they're much tighter again. They're clustered closer together, and they're hugging right around where the middle is at. With my third standard deviation, 99.7 now. So this is interesting because now my tails end inside of my spec limits. This is a good thing for me. When I turn on my bell umbrella, I'm still going to have those 3 parts per 1,000 outside of my tails. They're always going to be outside of your tails. Nothing you can do to bring them in. It's your law of nature. It's going to happen. However, these 3 parts per thousand typically, usually, normally hang out within that 4th sigma range. They tuck in really close. There's a little magnet on these suckers and they hang out right close to that 3rd sigma. Now, it's not impossible that something could still be out here, but it's less likely, less probable. With that said, I've got 0.15. I've got them hanging out here. They're outside of the bell, but in this case, they're inside of my spec line. So now if I'm making a safety-based product, I have much less risk here. And I might not like that. It still might be too much for me, depending on the type of product I'm making or the process that I have, whether it's a safety risk or a production risk. So I'm going to put my bell on another diet. I'm going to work on one of those 6 things: man, machine, material, method, measurement, environment. See if I can get her skinnier again. And whoop, there she goes. So now she's even skinnier. And again, that plus or minus 1 sigma, 68.4%, really now much tighter. My parts are really clustering in that center. They're hanging on in there. Within plus or minus 2 sigma, they're a lot closer. They range, in a much tighter grouping. And I still have those parts, 3 parts per thousand, are going to be outside of my bell umbrella, no matter what I do, no matter how fat or how skinny this bell is. There will always be those parts outside. Now, as I told you, they have a tendency, a higher probability to hang around that 4th sigma. So that 0.15 on either side, those bell umbrella parts are going to come out and they're going to be right there, typically in that 4th sigma range. And now you've got more wiggle room. So if you're dealing with a critical process or a highly significant feature, now you've got a little bit more room for your bell to maybe even shift a tiny bit to the right, shift a tiny bit to the left. And then in this case, you have some room because in the previous bell, let's see if I change it back here. If I shift this guy to the right any little bit, I'm going to risk having non-conforming product. I'm in a good spot. That's true, but I've got no room to move now. I'm stuck right there. If I move off of that center, I'm at risk. Whereas if I'm looking at this process, I've got a little breathing room. Now let's put the bell on a diet one more time. In this case, I can fit 5 standard deviations. I've got room for 5 sigmas between the average and the spec line. And 3 sigmas fit. So 5 divided by 3 is 1.67. That's how that calculation works. So now we've moved it one more time. We've put her on her last diet. She's on a liquid meal or something. I don't know what. And now it's super skinny. And with this, I've got room between the average and my spec line for 6 sigmas to fit. This is what we call 6 sigma quality. When there is physically room for 6 standard deviations to fit between the average and the spec line. And I can see that I have 6 sigmas of room. I've got 3 sigmas to my bell, and 6 divided by 3 is 2. And that's how this process is now. The whole bell can fit in here twice. From my bell umbrella perspective, my bell umbrella, those 3 parts are still going to be out there. They're like little bad pennies. They hang out every time. And when you're dealing with your plants, with your engineers on the design side, make sure that you're giving you enough room from your from your product specifications on whatever features you're dealing with, so that in your production process, when you industrialize, you have enough room for those parts to hang out and not get you in trouble. So that's the concept of 6 Sigma and CP/CPK. When we start out with an initial process, the very first time I run it, we have 2 kinds of process capabilities that we talk about: short-term and long-term. The initial, very first time I run this process, I'm on a machine or in an equipment environment. I've got my best operator running it. I've only got one person running it, maybe for one shift. I've got one set of raw materials. I've got one setup. I've got one set of environmental conditions. So this is really as good as it's going to get. My other features are at a minimum set of variation. I've got it's my machine really. Many people call your initial capability a machine capability. Maybe it is, maybe it isn't, but depending on the process, this can mimic a little bit more of the machine capability in itself. But you're holding all those other things generally constant when you run it for the very first time, when you do that initial process capability. And like I said, this is as good as it's going to get for the most part. On occasion, if you do something really significant to the process, you might get later a better process capability. It's possible. It's just not typical. With that said, I've got my initial process, but now I turn it on. Everything's good. I'm running at a 2.0. My bell fits in here 2 times. I'm a happy camper. But as I start introducing normal variation through material, through changeovers, through setups, through operators, through seasonality and different environmental conditions, as all of these other normal variations come into play, my bell will de-evolve. It will get fatter. I see it all the time, every time, everywhere. Very, very rarely does it get skinnier. So you have to be prepared for whatever you start with. It's going to get fatter later, and that's okay. It's supposed to. It almost can't not get fatter. So with that said, many people hypothesize that there's a 1.5 sigma shift in here. I honestly don't know if there is or isn't. I just know that it always gets fatter. The bottom line is you can't let it get worse than a ratio, a CPK ratio of 133. Or else those 3 little buggers that are out there, those 3 little parts, are going to cause you a nonconformance problem. And that's an issue. So whatever you start with, it's good. You want to start with that 2.0 or 1.67, especially if you're on a safety feature or a critical feature. And you can allow it to de-evolve over time, but it can't get worse than this 133. And if you set up and start at a 133 and it de-evolves, then you're in trouble. The process is not enabled to make all good product. So let's talk about some ways to figure out how bad is bad. We're going to look at some CPKs because we calculate those a lot, and we're going to help you convert those into parts per million. This is a one-sided CPK table, so only for half the bell, half the umbrella. So in this example, I have a process capability of 0.67. And how I read this table is I take my CPK of 0.67, 0.6 is the A dot B, going down to 0.6 here, running it across to the 07, and it says this bell is going to create 22,216 parts per million product. Typically, that's not good. People don't want that much risk. If I want to see what my actual percentage is, and this is only for one side, and if my process capability is on one side, it's only going to be for 1/2 of this bell, 22,216. And if I want to see what my actual percentage is, I divide these numbers by 10,000. And then that tells me I'm going to have 2.22% in this blue range that's on the outside of my spec line. For me to get the whole picture, I would need to double that because I have the same amount out on the other side. So I would have non-conformance results of about 4.4%. So when we deal with our managers and upper leaders, we're working with them to try to sometimes justify, why do I need an equipment fix or this kind of gauge? It helps me understand the expense. So if I know I've got 4.4% falling out, I can multiply that through an annual ratio of what kind of scrap that might be. And that could help me justify costing of new equipment to help fix the situation. Let's look at another one. In this case, I have a 1.0. And this is where our engineers really, really get hooked up, everybody. They don't know about that bell umbrella. They can't see what's not shown. Most of us can't. It's very easy to forget those 3 parts per thousand out of here, which is why CPK is often such a mystery for many of our people that are working in our production environments. So now I have a process capability of 1.0, and it's 1.00. So I'm going down to 1.00. And that says I've got 1,350 parts per million. Well, in a safety environment, that's not acceptable either. And again, that's only going to be on one side. So to make sure that I have it figured out, it's 0.135%. I would double that to 0.27%. So most people round that up to 0.3%, and that's why they say 3 parts per thousand. That's where that 3 comes from, where they're rounding up the 0.27. Let's look at a different one. The bell that we looked at when we first started out that had a CP of 2, it fit in there twice like this one does, but the CPK on the right-hand side is 1, and on the left-hand side was 3. So looking at this, we're back to that same position, 1.00. We're only going to look on the right-hand side because this is where we have risk. And we know that this is a 1,350 part per million risk for us. And it's only on the right-hand side. This is only where we have product risk. And then I would be dividing that by 10,000 for 0.14% out of spec. And again, depending on what the issue is, if a customer had a part out and they received it and it was too high, that's not a high probability, 0.14%. But if I'm making millions and millions, there's going to be some in there. What's that adverse effect that the customer experiences? Does it affect life? Does it affect regulations? Depending on what that effect is, maybe it doesn't matter on one side and it matters on the other side. So it's just going to depend on how the product is used and what its applicational impact is. And we'll look at one more. Here I have a process capability of 2.0. I'm looking at 2.00, so 2.0 all the way down, 0.00 here, and it ends up being 0.001. I divide that by 10,000. I have risk. It's not a big one, but there is risk. And this is as long as I'm not taking 100% of all of my featured dimensions. If I'm measuring absolutely everything, then you already know what you have and don't have. And again, this works if the process is normally distributed. You need to have that bell for these tables to be somewhat accurate for you. If you don't have a normal distribution, there's lots of things you can do to transform the distribution, or there are other tables, other ways to get an accurate sigma estimate so that you can get a more valid result here and truly figure out what your risk is. That's another session, and it's a lot of fun. So now let's look at sigma. How is sigma calculated? On the right-hand side up here, you see the actual formula, sigma, the standard deviation. It's a square root of, and this big epsilon here, that's a fancy plus sign in Greek. That's a fancy plus sign. You might want to follow this through with me on your calculators if you'd like. And what we're going to do is we're going to take each value that we have. I've got 3 samples here, a 2, a 1, and a 3. And I'm going to subtract it from the average. And the average right now is this blue 2. And I'm going to square that number, square that result. And I'm going to take the sum of all of them, of the first one and the second one and the third one. And then I'm going to divide it by n minus 1. Now, n is my sample size. That's how many readings I have. And in this case, my sample size is 3. And subtracting it by 1, and I'm going to hurt your heads because you're all statisticians. This is JD terminology. I call the n minus 1, I know it's degrees of freedom, but I call it the punishment factor. We get punished because we didn't measure all of the parts. And if I took this minus 1 away and I just divided by n, my sigma would end up being skinnier. It would be nicer to me. And I would think I have a smaller process. But if I am not taking the whole population of all of the parts in the process, then I have to put in some limitations to myself that I'm losing a degree of freedom here because I didn't take everything. So make sure when you're, whether you're using Excel, Minitab, SQL, SQC Pack, whatever software you're using, make sure you're using the right type of standard deviation. Typically, this is the go-to, where you have the -1, the n-1 in there. That's the most standard one that people use. It doesn't hurt anything if you use it. You're just more conservative if you do happen to have the whole process and you don't want to take away the n-1, it's giving you a fatter sigma than you may deserve. I'm only using 3 just for time. Typically, I would have a lot more samples, 30 samples, 50 samples, 100 or 1,000. So when I went to college, guys, girls, anybody on the call, when I went to college, first of all, I was the only female. But secondly, I didn't have a calculator to do these fun things with. We had to do it by hand. We had the plus minus calculators, but not the fancy standard deviation stuff at that time. So we were calculating sigma by hand. So you get to experience that at least once. So here the formula is written linearly, and we're going to go through the plug and chug. So now I'm going to plug in all the values, and we're going to chug through it. So I've taken my first value of 2, my average of 2, minus my first number of 2, 2 minus 2, and I'm going to square that. I'm going to do it again. My second grouping is my average of 2 minus my second value of 1. I'm going to square that. My third grouping, because I've only got 3 numbers, is the average of 2 minus my 3, and I'm going to square that. And I'm going to take all of that and divide it by 3 minus 1, 3 being my sample size. Moving on down to the next one. My standard deviation is 0. 2 minus 2 is 0, 0 squared. 2 minus 1, 1 squared. 2 minus 3, minus 1 squared. And then 3 minus 1 is 2. So now 0 squared is 0, 1 squared is 1, minus 1 squared is also 1. 2 negatives make a positive. And I'm going to divide that by 2. 0 plus 1 is 2 divided by 2. 2 divided by 2 is 1. And my square root of 1 is 1. So this is your exercise of how to get to 1 in a very painful way. Here's what the distribution looks like. I've got my 3 values. I've assumed normality in this case, just to run the numbers so that you could see the example. I have a 1, a 2, and a 3. So I've only got 3 pieces that I've looked at. My average is 2. My sigma is 1. And my formula is, my average plus 3 sigmas. My average is 2 plus 3 times 1. It's going to take me to a 5. And then my average minus 3 sigmas. My average of 2 minus sigma plus sigma plus sigma takes me to a minus 1. In this case, I don't know where my specifications are at, so I can't calculate a CP or a CPK. And, in real life, there would be a lot more values here. But just imagine how much fun you would have with, 30, 50, 1,000, a million pieces, dimensions, all the way running across this thing. Can be very traumatic to have to do. There's other cheater ways to do this in table formats if you're really a geek like I am. And it's so much fun. Anyway, this is just to show you how sigma works and that you can see how it then results in your process distribution from here. So now, this is where you get to have some fun. On the left-hand side are the formulas. On the right-hand side, pick your name. Whatever name you have, if your last name is A through F, G through L, M through R, S through Z. And in every case, the upper spec limit is 10. And in every case, the lower spec limit is 0. So the spec is from 10 to 0. So I'm just going to tell you now, upper spec limit minus lower spec limit, 10 minus 0. You don't even need a calculator for that, just fingers and toes. And then if your name is A through F, do these different examples, calculate the CP, calculate the CPK upper and the CPK lower. And while you all are doing that, I'm going to verbally talk us through this first grouping, just in terms of how to plug and chug the data. And then we'll go through all of the answers so that you can see if you got it right or not. So start plugging and chugging. In the first example, I have an upper spec limit minus a lower spec limit, 10 minus 0, as we already said, that gives us 10. And I'm going to divide that by 6 times my standard deviation, 6 times 2.5. In most places, that's 15. So 10 divided by that is going to give you your CP. To go to your CPK upper, you're going to take your upper spec limit, which is always going to be 10, minus whatever your average is. And the averages change from bell to bell to bell. And you're going to only divide that by half of the bell, or 3 times the sigmas. That would be for the upper. And then for the lower, you're going to take your average minus your lower spec limit. So 5 minus 0 in this first example. And again, your average changes in some of these. And you're going to divide that by the lower half of the bell, the bottom 3 sigmas. So hopefully that's given you enough time to plug and chug and have some fun during your lunchtime or wherever you're at. And we're going to go on and show the first example. Now, you don't need to take pictures of all of these until I get to the fourth one, which I'll have them all. But that's up to you. So in the first one, it's the 10 minus 0 divided by 6 times 2.5 equals 10 divided by 15, which gives me 0.67. The process capability upper and lower all both equal 0.67. And the reason why they're all the same is because the bell is centered. The bell is in the middle. As long as the bell is in the middle, all 3 values will equal the same. If the bell is not in the middle, like in sample number 3, you're going to get some pretty different values. And this is why CPK is so important. CP tells you what your process can do. So in this first case, it's 0.67. It can't do it. It's too fat. Even in the second one, it's still too fat. In the third one, it could do it, but the CPK tells you what it is doing. So there's can and is. The CP is telling you what it can do. The CPK tells you what it is doing. Going on to the next one, where we have the process capability of 1.0. 10 minus 0 divided by 6 times 167. 10 divided by 10 is 1. Fits in there one beautiful time. And again, this is where it's so deceiving, because you don't see those 3 parts per thousand outside of here. There was a lot of attempts to get the normal distribution drawn with 4 standard deviations so people could capture that 4th little sigma with those 3 parts in it. And the world is just too conditioned to the plus or minus 3 standard deviations. I don't see it changing, but it sure would help our engineering community, because you just don't see it. And unless you have that knowledge and applicational understanding of what it means, it gets missed a lot in real life applications. And in this case, since the bell is centered in the center, it's 111 all the way across. And in here, I'm going to have 0.27% non-conforming. In my third process, you guys that got to do this one, you had to do some extra work. The upper spec limit minus the lower spec limit, 10 minus 0 is still 10. 6 times 0.83 is still 5. And 10 divided by 5 is 2. So the bell fits in there twice, but we can see that it's clearly shifted off. On the upper CPK upper, we're going now into the skinny range from the average to the upper spec limit. And how many times does that upper bell fit? It only fits in there one time. You can see it. So I always tell people to draw these things out so that you can see what it looks like and see how it's sitting. And then how tight is your bell to the tail, or how tight is the tail to the actual spec line. This helps your engineers too when they're dealing with industrialization or trying to convert from prototypes into a real production process. On the last one, it's 2s all the way across, and this is our preferred distribution to start out with. So now, from a Taguchi loss function, the center, the farther away it gets from your target, the more expensive it is to run up until you have total loss. If it hits your spec, it's scrap or rework. I mean, you've got an extensive loss happening on either side if it goes beyond the spec lines. But even as it approaches the spec line, it's a less than optimal part. It should fit, it should function, but it has to match and stack with other things. And those other things may or may not be at their optimal condition. If I have a part on this side matching to a part on that side, it might not be as optimal as I like it to be. So all Taguchi says is the farther away you are from whatever your target is, the less optimal it is from a form, fit, and function perspective. So now we're going to flip gears. We're going to go into measurement system analysis. And in here, again, we're not going to do a deep dive into how to calculate a gauge R&R. We're just going to talk about the resulting error, the percent error that comes out of a gauge R&R. So when we measure or make an assessment of an item, we need to make sure that our result is correct. We have people taking measurements, and people are making a decision based on what they see or what they read. But also we have a lot of automated gauging going on, and that just happens without any kind of human intervention at all. And there can always be two kinds of issues that happen with any gauging system. We can have an alpha risk. This means we take a good part and we reject it. We put a good part in the reject bin. Oh, darn. So I remember alpha as, oh, darn, I just threw away a good part, or I'm reworking a good part. Customer doesn't have any bad thing that happens to them on this. It's our risk, the producer's risk, because I've just cost myself more money. Now I might have a higher price in my product because I'm doing this, but there's not a functional risk to the customer themselves. A beta risk, boy, that's bad. Betas are bad. And that's how I remember beta. Beta is when I accept a bad part and I don't know it. That's the key. Nobody really wants to intentionally accept bad parts. They've got a gauge, it says a value, they think it's in spec, and off it goes. But the gauging system itself has error in it. It has some little part where it might not be that exact value. And if it's not, that person can make an honest mistake and say, well, it says it's a 10, it's a 10, off it goes. But also, if it's an automated gauging, the same thing exists. Just because it's automated gauging doesn't mean that alpha and beta errors don't exist. They do. Typically, when we're looking at measurement system error, there's lots of different ways to do MSA, don't get me wrong. We try to look at two very high-level ones, the crossed gauge R&R, and that's the most standard, most typical that's out there. One instrument, 3 people, they're all measuring the same parts, over and over and over again. I want to measure the diameter of my ink pen. I can do this without destroying my ink pen, and I can measure it over and over and over again. And I can get a pretty good sense of how much error is in my gauging system. If it's a nested gauge R&R, let's say I have to do a bending test on my pen and I got to break it. That's when I'm doing gauge error analysis on destructive testing, something that I can't take the same reading on again. But either way, both of those systems have error with them. Now, when we talk about measurement system analysis, let's talk about how our data can vary. The first bullseye is I can have accurate and precise. My readings are tight and they're correct. They're precise. They're right there where the reading is supposed to be. That is handled by calibration, as it should be. So calibration takes care of that, and that includes bias, how far off I might be, and sometimes we intentionally set things. We have an offset on purpose. And then how is the gauging holding and stability over time? This third one is also accurate, but it's not precise. I've got a lot of scatter going on, but the average of my readings are accurate. So precision is about the error. It's about how well does that gauge function in this environment. I can have a perfectly, wonderfully, beautifully calibrated gauge and have it give me 100% wrong readings. I've seen it. I just saw one a couple weeks ago with a friend of mine. It happens a lot, more than you want to think. I had a process where they were applying coating to a product. It was a chemical vapor deposition coating. The coating was going on to a metal product, and it was how thick was the coating. So they had a little paint chip, and they would take the measurement device. They would calibrate it to the paint chip. Paint chip says, yes, it's this thick, and he's got a calibrated gauge. And then he puts it on the part. And now the gauge gives him a reading. It's this thick. And he says, oh my gosh, it's too thick or it's too thin. If it's too thick, it's got to go for rework. The paint has to be stripped off and they got to do it again. Or if it's too thin, they just run it through and they put more paint on. Well, the readings, unbeknownst to the operators, were 100% wrong. And you say, how can that happen? It went from calibration to this. And the point is that the parts were coming out of an oven and they're a metal part. And the parts were coming out at 100 degrees. And it was using magnetic induction to use to figure out how thick that paint was, using the frequency. And the magnetics were all screwed up because now the part's 100 degrees, the metal behind it's 100 degrees. So how the gauge was being used was improper for its application. And they were making lots and lots and lots of bad parts. They were sending them back for more and more and more paint. And someone got the brilliant idea, well, let's cut one in half and see on a microscope how thick it is. And they got paint this thick, and the gauge is saying, wow, my goodness, it's this thick. So they were getting wrong readings. And then, of course, they were really confused because once the part cooled off, if I measured it later on, I got a completely different reading, even if I measured it in exactly the same place. These kinds of errors happen a lot. So you have to make sure that precision evaluation, that error portion of Gage R&R repeatability and reproducibility is happening not only in your production environment, but in your gauge labs. I almost see no Gage R&R in gauge labs wherever I go. It's criminal. I've got a guy who's going to pull a gauge out of his pocket. They're not making hundreds and thousands of parts. They've got 2 prototypes, maybe 3 or 4, depending on how expensive they are to make. And they're just doing a couple of readings. And then based on those readings, they are deciding if the spec is sufficient, or they're setting a spec, and based on a couple of values that may have a lot of error in them. And then they could be making alpha beta errors to begin in addition to that. So it's pretty critical that Gage R&R be done in the laboratory when all those little pieces of equipment too. In addition to calibration, they do calibration very well, but it often gets missed. Your supply chain, you have to make sure that they have effective gauging systems. Now, it is allowed in the world to have 10% error. It's allowed. It's a global standard. So the measurement error of 10% is pretty common. Sometimes, depending on the type of process you have, you can even go up to 30% error. Imagine having a lab gauge at 30% error, and now they're trying to set your specs to this. It's beyond my logic. The third thing we look at is resolution. So I've got this clock on the wall here, and it says 10, 10, 35. So my resolution, I can discriminate my reading to the nearest second. Is it 10, 10, 35 or 34 or 36, plus or minus a second? If I take off the second hand, I lose my ability to discriminate in seconds. I can't read it in seconds anymore, but I can read to the nearest minute. So now it's 10:10, but is it 10:09 or 10:11? Now I'm within plus or minus a minute. If I take off my minute hand, I can only read to the nearest hour. Is it 10 o'clock, 9 o'clock, or 11 o'clock? And now I have to infer within that 2-hour range. So it's how well you can read the gauge. So a spec of 0 plus or minus 10, and I apologize, your gauge has to read to plus or minus 1 in this. So you need a little extra on this. So make a note. A spec of 0 plus or minus 10 needs to read to 0 plus or minus 1. That's how well it has to discriminate in our world today. And this is a global standard that your gauges must read to 10% of the tolerance being done. So let's move on. Let's see how this works. I call this the three-legged stool. There are a couple of more features that go into a gauging system. These are the big three in my mind. But if you're missing any one of these, if you're missing calibration, if you're missing gauge R&R, and if you're missing resolution, you cannot rely on that measurement system to give you a good result. You just can't. So why is an R&R critical to process capability? So we all know now that I have this distribution. It's a process capability of 1. It fits in there one time. I know I've got those 3 parts per 1,000 hanging out here, but now I have a 10% error gauge, which I'm allowed to have. 10% error, that's allowed. So if my gauge reads a 10, my operator picks it up, takes the instrument, it's a 10, good part. Off it goes into the good box. They're going to make the wrong decision 1/3 of the time. They're going to make a beta error 1/3 of the time, every time they have a 10. What's worse is the process is going to create 10s. The process is going to create 11s as well. So the process is going to be making big parts. You are guaranteed to make beta errors every time. You start with a process capability of 1.0 and you have a 10% error gauge. It's going to happen. Now, if I read an 11, my gauge, my person's going, oh my gosh, it's an 11. Oh, bad part. Puts it into the scrap bin or the reject bin. They're going to rework it or scrap it. They're going to do whatever they're going to do with it. And now, 1/3 of the time, he will have made the wrong decision. He will have thrown away a good part. But he doesn't know that. The gauge told him it was a 10 or an 11. That's what it told him. So he made an honest decision based on what it showed him. And in this case, the same happens with automated gauging. I remove the human out of the process. There's no guy here fiddling with the gauge. It's automated. It's electrical. You still have error in this system. And if your process is still this fat, you are still going to be releasing bad parts into your environment or accepting rejects. Both are going to happen. Now, if I start with a skinnier process, and here I have a process capability of 1.67. And in this case, my 1.67, my process cannot make a 10. It's not going to produce one. I have no 10s to find. I have no 10s to make an alpha or beta error with. My process is going to create 6s. It might create a couple 7s, but so what? In this case, if my gauge reads a 6, I'm guaranteed to make a correct decision. I can't accidentally accept a bad part. I can't accidentally reject a good part. And this is why when we're dealing with safety features, you need that minimum of 167 to start out with. If you are, and that you can't really go less than 1.33 process capability in your live applications. It's for more than one reason. It's not only to help you with that 1.5 that's going to hang out there, but it's also to help you with your gauge error. You must understand that gauge error is playing a big part of that. Now you can actually peel out and figure out how much of this is gauge error. You can figure that out pretty precisely. But still, from an operator perspective, from a machine processing perspective, whether it's automated or not, you still have that risk. Gauge R&R is needed everywhere measurements are taken. We need it in the engineering test labs. It's not just calibration, people. It's gauge R&R. They've got to do the R&Rs in the labs. It's quality testing equipment in your own quality labs. It's your suppliers doing them on their testing equipment. It's your maintenance gauges. When you're building your machines and your equipment and they're using their various devices, they use laser mics to set things. How do you know they've measured it right? So as you get into production, you're trying to, quote, dial things in. How do you know that those readings are correct? Your production test equipment, that's where we pretty much have this fairly well done. And then product gauging. So a gauge R&R is needed across the full product development process. So we did it. We had a rapid high-level overview of how CPK generally works. Hopefully you practiced with me. And then we connected that process capability to the Gage R&R percent tolerance aspect so that we could see and prevent ourselves from having alpha and beta errors. You are now all granted a new superpower to help make a difference in your business and with your customers with your knowledge. So what I'm going to do is I'm going to end the show and I'm going to keep the deck up. And that is the end of my presentation. And what I want to do now is to see what questions there are. Oops. Okay. Let's see what questions there are.
There was a lot of discussion and questions around the best metric and when the metrics are appropriate when it comes to CPK versus PPK. I wonder if you could talk just a little bit more about which one you should be using and when and things like that.
All right. So first of all, I'll give you a brief moment of education. Asian Pacific customers, many of the Japanese customers call them the other way around. So I try to use the word initial capability and long-term capability. Europeans and Americans usually use CPK and PPK the way we do it. But the Asians do it in a different way. It's the same formulas, it's just reversed in terms of which one's which. But for me, I'm always looking at the long term. I'm always looking at the CPK long term. For me, that's because that's what I'm dealing with. That's my real life. I like to make sure that it's really tight. Now, you don't have enough data when you first run, when you first start, because you've got one run or two runs, or you don't have enough data to do a true, within variation analysis. Nevertheless, the formulation is the same. For me, JD, I hang out with CPK, meaning the long term.
Does it have to be in statistical control for you to use that metric?
It should be. That rarely happens. If you read enough books, you'll find that you are never, ever, truly, ever in statistical control if you want to get very theoretical about it. I say, is it close enough? I'm looking for shifts and trends. If I've got a very tight process like this one up on top, I'm pretty much not going to look too closely at micro, the micro levels of statistical stability in those. If it's a fatter process, then I'm going to take that much more into consideration. So for me, I'm looking first at the overall process and how well it fits. And I'm looking at that distribution. When you look at a histogram, you can't see how it's going over time. You need to look at both. You need to see how it's going over time to see if you have shifts, trends, high spots, low spots, things like that. And when you're and there's so much programming in place nowadays that your computers can do it for you in a heartbeat. So I do look at it. If the capability is not great, I pay less attention to it if the capability is super good, 2, 3, 4, 5 level. But that's me.
Thanks. I think that was very clear. A lot of good comments on the webinar, and I think we've reached the end of our time for today, but looks like it was well received, and I just want to thank everybody for joining and thank JD for this wonderful presentation. Thanks so much.
Hey, thank you all for joining. Have a great day. So Jenny, are you going to stay on for a few minutes?